Hello everyone, this is Mike Dowding with the SD Mines Physics Department. We're starting a new chapter today, Chapter 9, which has two main topics. The first of which is center of mass. The second, which will be covered in later videos, is conservation of momentum. And with our center of mass portion of this chapter, what we first want to do is discuss the idea behind center of mass. As it kind of sounds, if we have a mass and we look at the center point of that mass, then is that necessarily the center of the mass? And the answer to that could be yes, if the density of that material is uniform. Meaning we would have to have the same amount of mass per unit volume everywhere within the material. And if we do that, what that means is that if we were to bisect this material, then we would have the same amount of mass on one side as we do the other. And then the center of mass for our object would have to lie somewhere along that bisector. But then we can go through and we can bisect this object as many times as we need to, and where all of our bisectors intersect is where our center of mass is going to lie. And that's pretty easy to do if we in fact have uniform density throughout the material. If that's not the case, if the density is not uniform, then we're going to have to consider some other way of figuring out where the center of mass for this system is. Another problem is what happens if we have a mass that isn't necessarily symmetric, like what we have up here with the sphere. What happens if I have something that's more like a potato? It's not so simple to figure out where those bisector cuts should go. And so we'll need to discuss what to do in cases like that. But before we get to those larger 3D systems, we would like to consider a system of particles. And then if we can figure out how to find the center of a mass of particles, then maybe we can apply that back to the larger three-dimensional systems that are going to have tens of thousands, if not millions or billions of individual particles. But one step at a time. I'm going to set up an XY system, and I will place 3 particles in this system. The first one I'm going to place right at the origin, so this will be mass 1, and we'll let that be a kilogram. Mass 2, we will place that right up here, and so mass 2 will be 2 kilograms. And we'll go ahead and label these mass 1, mass 2, and then for mass 3, we'll go with that, and we'll put mass 3 right over here, and we'll make mass 3 3 kilograms. So a system of particles, and given the XY axes, we have the ability to label the ordered pair for the location of each of these masses. And ultimately, since we're looking for the center of mass, and I'm gonna shorthand this to COM, center of mass. I'm looking for a physical location that the center of mass will exist at. So we're looking for some ordered pair of x and y position, and that's going to ultimately come from a combination of the mass values and where they are currently located. So mass 1 has its location at the origin, 0, 0. Mass 2 is located at x equals 2, y equals 4. And mass 3 is located at 1, 2, 3, 4, 5, x equals 5, and y equals 1. Okay, so that's all the information that we're given about this system. And now it's our job to find the numerical values of the center of mass for the system. And as the name implies, we're going to be looking for a point somewhere within the center of where all of these masses are placed. And if it was a system that consisted of 3 identical masses, all 3 being the same mass value, then our center of mass would be the geometric center of the system. Problem is, the masses are not the same. And what I would like you to do, just as a bit of a thought experiment, imagine that this XY graph that we have here is a 2-dimensional tray, and you're placing food items on the tray. So maybe mass 1 is a salad, mass 2 could be a plate of pasta, and mass 3 could be a large pitcher of iced tea, or whatever you want it to be. So we have 3 different items of different masses. Now obviously this tray is very large. I've put the scale at meters, but if you could imagine a tray this large, and you're trying to find a point on the underside of the tray where you can balance the tray without everything tipping over and falling. And if you've ever worked in food industry, or you've ever been to a restaurant and you've seen someone drop or spill a tray, this is exactly what we're going for. So where is that special spot underneath the tray where we have to place our hand to balance everything? That's what we're looking for. And if you've ever tried something like this, you know that you have to place your hand closer to the heavier object on the tray. In this case, it would be the 3 kilogram. And that's my attempt at drawing a hand there. So what I'm going to do to help us in understanding this concept is I'm going to draw an area where I'm guessing that the center of mass should be located. And to do that, I'll start by just connecting the 3 masses with some lines. And if everyone is in agreement, the center of mass for the system should be somewhere inside that triangle that I just drew. That goes with the idea of our point being somewhat centrally located in the system. Now keep in mind, this is an estimate, or a guesstimate as I like to call it, and this is just to help us narrow down the area where we expect the center of mass to be located. We will follow that up with some actual math to give us an exact location, and then we'll see if our guesstimate region matches up with the actual. So to help us in doing that, I am going to start at mass 1, and I'll draw a bisector line that goes across the triangle. And a simple question, which side of that bisector should the center of mass be located? And if you answered below the line, you would be correct, because below that line is where mass 3 is located, and mass 3 is larger than mass 2, so we need to have more mass towards the bottom side of that triangle. So that means the whole top half is out. Then we're going to try that same trick starting at mass 2. We'll draw a bisector line through the triangle and ask the same question. Which side of that bisector should the center of mass be on? And again, it should be closer to mass 3 because mass 3 is bigger than mass 1. So this portion is out, and I'm going to fill in some more of that there. So our triangle is getting smaller by the moment, and the last thing we have to do is draw a bisector from mass 3 and ask the same question. Which side of that bisector cut do we expect the center of mass to be on? And in this case, we're comparing mass 1 and mass 2 with that bisector. Mass 2 is obviously the larger of the two, and so this bottom portion is out, leaving us with this portion of our guesstimate region. So this is where we're expecting the center of mass for the entire system to be located. Now there are still plenty of points inside that region, but at the very least this will give us an idea as to whether or not our final answer is valid. So now comes the point where we have to start putting the math together. With all those bisectors that we made, we kept saying which side should the center of mass be on, and every time we asked that question, the answer was based on which side had more mass. And so the more mass a given particle has, the more influence it has on the system. In other words, that mass has more weight in terms of where the center of mass should be located. And I don't use this term to mean weight in the physics sense. I just mean that the mass is going to weigh more heavily in the math. The heavier the mass, the more it is going to influence the mathematics. And so another thing that you might notice is when I drew all of those bisectors, the bisectors all intersected at the geometric center of the system. And we said that's where the center of mass would be located if I had 3 identical masses. And to find that location, what I would do is I would just average together the x and y positions of all of those masses, and I would get that center point in the triangle. Can't spell average. Well, if we average all of the positions of our masses, we're not going to get the center of mass for the system. What we have to do is combine these two ideas. We want to average the locations of the masses, but at the same time, we need to weigh the contributions of each of those masses. And this may be something that you've run into in a previous class. We're going to do what's called a weighed average. So you may have had a class in the past where, say your test scores were 80% of your total grade and your homework was 20% of your total grade, even though all semester maybe you only had a total of like 50 test questions and you had 1,000 homework questions. If a point were a point, then that is not the same percentage distribution as what we have over here. Yet, if we apply that weighed average process, we give more influence to the test score as opposed to the homework score. And that's exactly what we want to do with these particles. We want to give more influence to the heavier masses and less influence to the lighter masses. And the way that we can do that, we're gonna start with a regular average, and we'll start with just the x values. So we want to find the physical location along the x-axis where our center of mass is located. And then we can come back and we can do a similar process for the y component. So as I said, we'll start with a regular average. And for that, we add up all our values. So we're going to add up all the x values of our positions for mass 1, 2, and 3. And then the next step in the averaging process would be to just divide by the number of entries that you're using. And so if I added all these up and divided by 3, that would get me a value. Except if I do that, I'm going to get the geometric center, and I don't want that. I need to incorporate the masses of the systems. And the way we'll do that is we're going to take each location and we will multiply them by the mass that is present at that location. So now each of those locations is being weighed based on how much mass is located at those positions. But now if we look at the units, all the units on the right-hand side are a combination of kilogram and meters. And I just want a location. I just want meters for the final answer. And so the last step in the weighed average process is that I need to weigh the influence of each mass against the total mass of the system. And the total mass of the system, well, that's just mass 1 plus mass 2 plus mass 3. And by dividing by the total mass of the system, now the units will work out, because I'll have meters on the left and I'll have kilogram meters divided by meters for all 3 of these terms on the right. So what does dividing by the total mass do? Well, keep in mind that every one of these terms is being divided by the total mass. And so if we were to look at each of the top masses, sorry, wanted to get a different color there. There we go. If we take each of the masses and divide them by the total masses, mass 1 divided by the total mass. Well, let's see what we have for total mass first. Total mass is 1 plus 2 plus 3, which is 6 kilograms. So mass 1 over total mass is 1 over 6, and that's being multiplied by x1. We have mass 2, which is 2 kilograms over 6, multiplied by x2, and mass 3 was 3 over 6 times x3. And here's where we can actually see the weighing process. Mass 1 is contributing to 1/6 of the total mass in the system. Mass 2 is contributing to 2/6, or 1/3. And mass 3 is contributing to 1/2 of the mass in the system. And if we add up those three contributions, 1/6 plus 2/6 plus 3/6, we get 6/6, or 1, which is equal to 100%. So what we've done now is we've taken the location for mass 1 and we've multiplied it against the percentage of the total mass that it accounts for. And then we took the location of mass 2 and we multiplied it by its percentage, and then mass 3 times its percentage. Now I usually don't write out the expression with those fractions, but that's just to show all of you how this weighted average process is working. Instead, we have mass 1 times x1. So let's put the values for everything in here. Mass 1 is a kilogram. x1 was 0 because it was at the origin. Mass 2 is 2. x2 is also 2. And mass 3 is 3. x3 is 5. All divided by the total mass in the system. So we have, what is this, 19 over 6, which is going to be 3 1/6, or if we convert that and it's going to give us 3.17 meters. So 3.17 meters. If we come back up to our diagram and we draw in a line on the x-axis at 3.17 meters. So here's 1, 2, 3, and a little bit past that, right about here. 3.17. Right there is where the center of mass for the system is going to have to be located. Now there are a lot of points on that line, but the important thing is that that line is passing through the guesstimate region that I talked about. And so we're going to go back and do the same approach, but for the y-axis. And it's going to be the same equation as what we did for the x-axis, except we're going to use the y components of position for each particle. Alright, so mass 1 is still 1. y1 is 0, because we're at the origin. Mass 2, y2 is 4. Mass 3, sorry, this should be y3, not y1. y3 is equal to 1. All divided by the total mass of the system, and this is giving us 11 over 6. And that comes out to be 1.83 meters. So back up to the diagram. 1.83 meters is just a little bit below the 2, so maybe right about here. And we're going to draw a line across that, and where the two lines intersect is the center of mass for our system. Now my line went a bit askew there. Let me redraw that and make it look more like it's try to make it look more horizontal if I can. There we go. So we have the location 3.17 comma 1.83 is the center of mass for this system of particles. So now that we've figured that out, let's take a moment and we're going to clean up these two equations that we've made. We want to generalize what we have in these two equations. In the bottom of the equation, the total mass comes from summing up all the masses in the system. So the bottom part can just be represented as a summation of the masses. In the numerator, we also have a summation, but it's the summation of the products of each individual mass times its individual location. And so this is going to be our equation for finding the center of mass X component. And I caution you, I see a lot of people look at this equation and they see sum of mass in the numerator, they see sum of mass in the denominator, and they go, oh, we can cancel that out, and all that's left is the sum of the X components. And that is really wrong, because if you were to add up all the X components, and that's all you did, you would get 7, which is way out here outside of our guesstimate region, and so that's not correct. We need to keep in mind that this summation down here, we need to complete each individual summation before we start tackling any of the division. So summations first, and then division. And then down here for the Y component, it's really the same equation, it's just that we've replaced the X's with Y's. So each mass times its individual location along the Y-axis divided by the sum of all the masses in the system. And that gives us our center of mass along the Y-axis. Well, that was a 2D system. What happens if you have a 3D system? Well, if you have a 3D system, I guess that means you have a Z-axis somewhere. But that's not going to change the structure of these equations. We're still going to have summations of each individual mass and Z positions over the sum of each individual mass. So in case you do run into a 3D system, there you go. It's really just the same equation written 3 times. You've just replaced X with Y and Z when required. Alright, so now we know where the center of mass for our system of particles is located. We have values that tell us that. So the next step that we want to consider is what happens if all of these masses start moving. So they're not going to retain their current position. They're going to move from one location to another location. And we call that displacement. And what I'm going to do for this next section of discussion is I'm just going to work with the x component of center of mass. And as you can see, the equations for y and z were exactly the same. We just had x or y or z. So if I can figure out how things are changing in terms of displacement on the x-axis, I can very easily come back and apply that same knowledge to the y-axis and the z-axis if necessary. So let's go back to day 1 of our physics class, where we defined what it meant to have displacement. So there was going to be some final position minus some initial position. And we want to apply that idea to the center of mass. So if all of our masses were to displace, so mass 1 displaces, mass 2 displaces, mass 3 displaces, so on and so forth. It should be an N. Well, that's going to tell us how the center of mass for the system displaces. And the way that we can justify that is we can take x initial, sorry, I wanted to highlight that, not cross it out. We can take x initial and we can say, all right, the initial center of mass location will be based on the sum of each individual mass times all of the individual initial locations divided by the total mass. And the final center of mass location will be dependent on where each of the masses finally ends up. And then we can take the difference in the two. Well, taking the difference in these two terms means taking the difference in the numerators. The denominators for each of these terms is the same. They're the total masses of the system. And if we were to write this out as mass 1, x1 initial, mass 2, x2 initial, so on and so forth, the only terms that can be combined between the two summations are going to be the terms that have the same masses. So when I take the mass 1 x1 final and I subtract the mass 1 x1 initial, what I get is mass 1 times the change in position for mass 1. And then when I take the difference in the next set, what I end up with is mass 2 times the change in position for mass 2, and so on and so forth, until eventually we get back to a summation that looks like this. So that's how we find the change in position for a center of mass. Long story short, all we had to do was incorporate a delta into our expression. Alright, so now we know that our mass, our center of mass, has displaced. The next step is to ask the question, how fast did your center of mass displace? In other words, displacement over time equals velocity. So as our center of mass is moving, how fast is it moving? And do keep in mind that everything that we have right now is just for the x direction. And so all we're going to get out of this is the x component of velocity for our center of mass. If I want the y component, then I can go in and change all my x's to y's. If I want the z component, I change all my components to z's. Well, I have taken the delta x center of mass and I've divided it by time. First rule of algebra says what I do to one side I have to do to the other. So over here on this side, I have to take my expression for change in center of mass and I have to divide that by time. So I'll sneak in a delta t there. And now the question is, what do I pair this delta t with? Over here it was pretty straightforward. I just paired it with the delta x because that was all there was, and I got v center of mass. Well, let's try pairing that with all the individual x positions of our displacements. If we do that, this fraction here that I just circled, the change in each individual position divided by time is going to result in the individual x components of each mass. And we still have our total mass term underneath. And so there's the equation for how the center of mass is going to move along the x-axis. It depends on how fast each individual mass moves along the x-axis. All right, so I'm going to start circling some of these equations along the way. So this is our center of mass expression for the x-axis. This is our displacement for center of mass on the x-axis. This is our velocity for center of mass on the x-axis. And I should probably put in my specifics for these summations. I think by now we know what they are. Everything's going to go from 1 to n. So if I forget that notation in a future portion, you can just make the assumption and plug it in there. All right, so that's velocity. What comes after velocity? Well, after velocity comes acceleration. And if we have an object that is changing its velocity with respect to time, we call that acceleration. Again, we're only working in the x direction, so that's going to be our x component of the center of mass acceleration. We have divided our center of mass velocity by time. So first rule of algebra says what you do to one side, you have to do to the other. And just like over here, I have delta v over delta t equals a, so delta v over delta t is going to equal a. Except that it is the x component of acceleration for each individual mass. Now maybe you're starting to catch on. Really, we're seeing the same equation utilized again and again and again. The only thing that we've done is we've updated the position term for a velocity term for an acceleration term. And then if we need to, we can go back and we can replace all of the x's with y's or z's, depending on which axes we're working in. But now we have an equation that tells us how the center of mass for a system will accelerate along the x-axis. So what do we have here? Well, there's 4 equations. We've got number 1, number 2, number 3, number 4, but really they're all of the same construct. They're all using the same summation approach, which is a weighted average. And all we've done is updated the equation for the new term, whether it was position, displacement, velocity, or acceleration. So we really don't have a lot of new equations. It's just the same equation repurposed for position, displacement, velocity, or acceleration. And so there's 4 equations related to center of mass for the x-axis. Now consider the same 4 equations written for the y-axis. And all you have to do is go in and we just change the subscripts from x's to y's. A sub y. And then if you have a 3D system, well, okay. We kind of know what has to be done now. We're just going to go back to those 4 equations and we're going to update them for z's. Now that's a lot for one topic, but now we have really everything that we need to go back and apply this idea to a solid 3-dimensional construct. And before you think that we're going to do a summation that involves millions and millions of particles, the answer is no, we're not going to do that. We're going to go back to this idea of having uniform densities within our masses, because if we can come back and take, say a slab of some kind of metal, and we can say with some certainty that that metal has a uniform density, then we can come in and we can start making some of those center cuts, and we can use the symmetry of the system to help us locate where the center of mass is. So that's not too difficult. I'm going to lead us into an example problem here. Let's say that we have a brick of some kind of uniform material. It can really be any material you want. Maybe it's a gold brick. And if we had to, we could look up the density of gold. But all we know for right now is that this brick has a length of L, a width of W, and a height of H. Now, if it's a real high quality brick of gold, then the density of that gold brick should be fairly uniform. In fact, that's what we're going to work with here. So that uniform density means that we have the same amount of mass per unit volume everywhere inside that brick. and I want to know where is the center of mass for that brick. And at this point, you can probably say, well, it's right in the center. And we would be justified in saying that because of the uniform density. But we should probably put a little bit of effort into this just so we can convince any of the skeptics out there. So here's what we'll do. We'll try those center cuts again. So I will cut this bar in half along the width. And if we do that, given that the density has to be uniform, will the mass of each piece be the same? And if we cut this in half right along the width, then the volume of the left-hand piece should equal the volume of the right-hand piece. And because our density is uniform, then the mass on each side of the cut should be the same. And that's the idea behind center of mass, is that we want the same amount of mass on all sides of us. So we know that the center of mass has to lie on that center cut, which would be W/2. Then we try the same thing along the length of the brick. So I'll go halfway down the length of the brick and we'll cut it in half. Do I have the same amount of mass on either side of that cut? And because our length was cut in half, we've got equal lengths on each side. We should again have the same volume for the front and back pieces. We have a uniform density, so both the mass of the front piece and the back piece should be the same, and so the center of mass will have to lie on that cross cut as well. And that cross cut is at L/2. And you can see where we're going with this. The last thing to do is to cut this brick in half along the height. So we'll cut it in half right along the height. We have, again, the same amount of mass on the top and the bottom. And so the center of mass has to be at H/2 for that cut. Now we put all three of those together. So we've cut this thing in half along the width, along the height, along the length, and all three of those cuts are only going to intersect at one point, which would be right in the geometric center. And that point is right here. Those are the three physical values of where the center of mass for that brick is. And you notice that I didn't even have to go and look up the density of gold. All I had to do was use the idea that we had uniform density and then just keep track of the dimensions of all of our crosscuts. All right, that's pretty straightforward. But now, what do we do if we have an object that is not quite so symmetric? So let's say you're working on a project one day and you need a piece of sheet metal, and so you go into the storage room and you find this piece of sheet metal, but somebody has already been at it and they've already cut it up. In fact, we'll make a few more little cuts there. Whoops. Alright, so this is the piece of sheet metal that you pull out, and you're thinking to yourself, whoever these people are, they're not very considerate. But now that you know about this idea of center of mass, you're curious. You want to know, where is the center of mass for this piece of sheet metal? And so we'll go ahead and figure that out. I'm going to make one more alteration here. I want to bring this side up just a little bit. There, that'll be the final drawing for this. I promise I won't make any more adjustments. All right, well, the first thing that we want to be sure of with this example is that we have a uniform density. Now this piece of sheet metal, whatever it is, if it's aluminum, steel, if it's some kind of composite material, that's fine, as long as the material that they used, they mixed it really well so that we have a uniform density. Otherwise, if this material has a lot of holes in it, or vacancies, cavities, impurities, a lot of that stuff will throw off the density, and then we wouldn't be able to use this next approach that we're going to try. Next thing we need to know is the dimensions of our object. So I'm going to go through here and I'm going to write out what I think the dimensions are. We'll say that this is 5 centimeters, 5 centimeters, we'll do 5 centimeters, 5 centimeters. We'll let this be 3, this can be 5, we'll let this be 3. We'll do 6 centimeters for this side. We'll say 5 centimeters for this side. We'll do 3 centimeters for this side. And so I believe that would make this top length 8 centimeters. We already have 6 right here. And then 5 minus 3 would be 2. So yeah, that top piece should be 6. And then we have 3. This actually looks more like 3. So 3, 3, and 3, so this should be 9 centimeters. Okay, so we need to make sure that the measurements of the top match the measurements of the bottom, and that the left match the right. So hopefully I got everything correct. I don't have the luxury of having you double check my work, but we'll find out here eventually. And for that, all we have to do is grab a ruler or take out a measuring tape and measure the sides. Because like we said before, if we know that we have uniform density, really the only thing that we have to keep track of is the volume of our object. And so, well, this piece of sheet metal, it's a sheet, and if it's a good piece of sheet metal, it should be the same thickness all the way through. You don't want to go and buy a piece of sheet metal and it's warped, and that's not going to cut it. So we're going to insist that the sheet metal have a uniform density, and so that thickness or depth or whatever you want to call it, we'll let that be the z-axis. And if we need to assign a thickness to this, we'll just go ahead and assign it a thickness of 1. Not 1 centimeter, but just 1. So one for uniform. Okay. And that means we just need to focus on the x and y values of the piece of sheet metal. Now the next thing I'm going to do to help us out is define a reference frame. And I will place this bottom left corner at the origin of our reference frame, because when we go to find the center of mass, I need x and y components that I can label as being the center of mass for the system. And so now if I need to say this other corner over here, if I had to define the position of that corner with respect to the origin, I could do that now. That would be 13, 14. So I just add up everything along the x-axis until I get out there, and everything on the y-axis until I get up there. Alright, so that's, and we don't actually need to know what that point location is. Again, we're going to be concerned with the dimensions of this asymmetric piece of sheet metal. Now, it would make our lives so much easier if this piece of sheet metal had not been cut up into all of these pieces. If we had a nice piece of sheet metal that was 13 by 14, then we could just do those half cuts and call it a day. But like we said, somebody's already been at this. We don't have the symmetric shape that would make our lives so easy. I can't just come in and start cutting this thing in half because I don't really know what half is. But could we take the idea of cutting up these symmetric pieces and pairing it with the particle example? So up here where I had masses 1, 2, and 3, could I somehow figure out a way of representing this as a system of particles? And at first you might say, well, this piece of sheet metal, it must have billions of particles in it. I don't want to do that. But here comes the idea behind center of mass. What if we were to segment this asymmetric shape into symmetric pieces? Now, I'm not saying go in there and cut it up into symmetric pieces. I'm just saying map out some symmetric areas. Like right here is a symmetric segment, and I could very easily find the center of mass for that segment. Likewise, over here is a symmetric segment, and it would be very easy for me to find the center of mass for that segment. And then we've got this other area here. Now, how you segment the region doesn't really matter. You can cut this up into as many pieces as you want, but I will warn you, the less pieces that you make, the less math you have to do. And so the way I see this, even though you might you might have a different idea as to how you want to segment this piece of sheet metal. I'm thinking the smallest number of segments that we can get away with is 4. You can have more than 4, but you're gonna end up with more math as a result. But regardless of the way you segment this system, the center of mass still has to be at the same location, regardless. Well, let's see what we can do. We've got 4 different segments here. I'm going to call these mass 1, mass 2, mass 3, mass 4 respectively. And I can find where these center points need to be located. So mass 1 needs to be located at 2.5, 4.5. And so, all I've done is I've taken those side measurements that we used. This purple rectangle that I'm calling mass 1 has side lengths 5 by 9, so our center point is going to be at 2.5, 4.5. Mass 2. Okay, so mass 2 is up here. And it has side lengths 8 by 5. And before you jump in and say 4, 2.5 as the coordinates, keep in mind that we have to measure from the origin. So I need to, first of all, travel out 5 centimeters along the x direction, and then add the extra 4 to get to the half point. So 5 and 4 is 9. And then I have to travel all the way up the 9 centimeters so that I can add the extra 2.5, and that would get us to 11.5. For mass 3, so mass 3 is right here, and it has side lengths of, and so here's the tricky part. So I know that the vertical side length right here is 3, and even though it may not look like it, I've got this portion, which is the difference in 8 and 5, so this would be 3 as well, even though it doesn't look like a square. That's what I get for doing a freehand diagram. But so that means that the center point would be at 1.5, 1.5 for mass 3, but then we have to add from the origin. Adding from the origin, we have to come out 5 centimeters. Sorry, that should be red. So we're doing mass 3. So I come out 5 centimeters plus an extra 1.5, 6.5. And then we have to travel up 3 centimeters, another 3 centimeters, and then 1.5 centimeters, 7.5. Okay, one more. Mass 4. Where is mass 4 located? Or where is its center of mass located? Mass 4 has dimensions 3 by 6. So we need 3 by 1.5. is its center point, but measured from the origin. So we have to come out 5 centimeters and then add an extra 3 to that. 5 and 3 is 8. And then we have to measure up 3 centimeters and an extra 1.5 centimeters. So 4.5. Alright, and this tells us the physical location of each of those symmetric segments. So how does that help us? Well, now I know the x and y components of all of those masses. And so we can take that information and we can plug it into the equations that we made up top that tell us what the center of mass for a system of particles is. The way this is going to work is we're going to assume that all of the mass for mass 1 has been concentrated into that point. All of the mass for mass 2 has been concentrated into that point. And for mass 3, it's all been concentrated into that point. Mass 4, it's all been concentrated into that point. So we've gone from a asymmetric system to a system with 4 equivalent particles in it. And this is where we get the idea behind center of mass. We want to use the idea of the center of mass as a substitute. So we've taken these 4 symmetric segments, we've found their individual centers of mass, and then we're going to use those in a particle expression. And because we know where the center of mass for each individual particle exists, we can now plug that information into these center of mass expressions to help us find the center of mass for the entire construct. Well, but that means I need to know the mass of each segment. Or do we? Because we said we have to have uniform density. No matter where I'm at, I have to have the same amount of mass per unit volume. Well, not every piece has the same volume. And that means not every piece can have the same mass. But every piece must have the same density. So I can take mass 1 and I can say mass 1 divided by the volume of mass 1 has to equal the uniform density, just like mass 2 divided by the volume of mass 2 has to equal the uniform density. And what we're going to do here is we're going to make a substitution for each mass using the volume that each mass is taking up. And each of those volumes times the uniform density has to equal the total mass in the system. We also need to know the total mass of the system. Well, that's going to be rho times all of the volumes. Okay, we can do that. And this video is getting kind of long, so what I'm going to do is I'll go through and I'll do everything for the X column, and then I'll let you, as a side exercise, work out what the Y component for the center of mass for this system should be. So for X component, we need each individual mass times its individual location. So mass 1, x1, mass 2, x2, mass 3, x3, mass 4, x4, all divided by the total mass of the system. Now for each one of these volumes, up here, density is still technically three-dimensional volume. Let's take a look at mass 1. Mass 1 has dimensions of 5 by 9 by 1. So we have 45. We can either call it square or cubic centimeters, but I'm just going to go with 45. Mass 2 has dimensions of 8 by 5 by 1, which is 40. Mass 3 has dimensions of 3 by 3, which is 9. Mass 4 has dimensions of 3 by 6, which is 18. So that means the total mass of the system is the combined volumes times the uniform density. So I'm going to add up all of these values, and I get 112 row. Alright, here we go. Mass 1 was 45 rows, located at 2.5. Mass 2 was 40 row, located at 9. Mass 3 is 9 rows, located at 6.5. And mass 4 is 18 rows, located at 8. All divided by the total mass, which is 112 rows. And if you are waiting for the density of this piece of sheet metal, sorry to disappoint you, but it is not required, because every term on the top has a row, and we have row down on the bottom, and so the density of the material is not required. All that was required was that the density be uniform, so that we could use this little trick. Okay, number crunching time. 45 times 2.5, 112.5. We've got 40 times 9, which is 360. We have 9 times 6.5, 58.5. 18 times 8 is 144. And that's all going to be divided by 112. I'm going to add up everything in the numerator. And I'm getting 675 divided by 112. So the center of mass along the x direction needs to be at 6.03 centimeters. So 6.03 centimeters. Let's find out where that is, and I'll put a big green dot, or I'll put a green line there, I should say. So from here to here is 5 centimeters. I need 6.03, so we'll come out to right about here. We'll say that that's 6.03. So right there is where the x component of the center of mass needs to lie. And I know I said I'd make you do it, but what the heck. I'll go ahead and put in the values and we'll find out what the y component is, just so there's no second guessing. So y component, center of mass, m1y1, m2y2, m3y3, m4y4, all over 112 rows. So m1 was the 45 rows, y1 is 4.5, m2 was 40 rows, y2 is 11.5, m3 is 9 rows, y3 is 7.5, and m4 was 18 rows, 4.5. So again, we have rows with each term on the top. We have rows with the term on the bottom. And I'm getting 202.5 plus 460 plus 67.5 plus 81, all over 112. Add everything up in the denominator. And I'm getting 811 over 112, which is 7.24 centimeters. So 7.24 centimeters. We need to come up roughly 7, which would be, let's see here, there's 3, there's 6, or actually here is 6. So all that should be 6 plus an extra 1. So right about there is where our y component is. Right here is where our x component is. And I'll put a nice big red X right there. So it's almost in the same place as where the center of mass for mass 3 is located. But now we have exact values. I know that the center of mass for that chopped up piece of sheet metal has these coordinates. And it, maybe if I even carried out the decimals a little bit further, maybe we could take this piece of sheet metal and balance it on a stick or something. You can wow your friends by being able to find that center point. Now, physically, you could probably do a trial and error and find where that center point is, but mathematically, this is the way that it would be done. We would take our asymmetric system, break it up into symmetric pieces, use those to construct a system of points, and then use our weighted average approach to find the center of mass for the system. Alright, so this is a pretty long video, but everything in this video should cover the first half of Chapter 9, which is everything to do with center of mass, whether it's particles, solids, position, velocity, acceleration, all of that has now been covered. So, thank you for your time. I'll see you at the next video.